The framework is general, now applied to the problems that traditional methods struggle with: non-identifiable parameters, inverse problems, and multi-scale dynamics. In traditional parameter estimation, you fix the model structure, plug in data, and optimize parameters. If a parameter is non-identifiable, the data can't distinguish between different values. The optimization gives an arbitrary answer or fails to converge. In a PINN, the ODE parameters are learnable alongside the network weights. The physics loss constrains the parameters through the ODE structure, and the network smoothness provides implicit regularization. A parameter that is non-identifiable in traditional fitting may become practically identifiable in a PINN because the neural network enforces physically plausible solution shapes that exclude parameter regions that produce implausible dynamics. Inverse problems, given observed data, infer the underlying parameters, or even the governing equations. In pharmacokinetics, given sparse concentration measurements, infer clearance and volume of distribution. The PINN solves the forward problem, predicting concentrations over time, and the inverse problem, estimating PC parameters, simultaneously. The same optimization that fits the neural network to the data also fits the parameters to the physics, ORD and inverse in one framework. Your GBM QSP model, 13 coupled ODEs describing DNA, EC inhibition, middle silencing via Roftrina, GIX recruitment, and ERG signaling. 3 parameters, KGBM prolif, KERG activate, KXGR internal, were flagged as non-identifiable by profile likelihood analysis. A PINN for this system, 13 neural network outputs, 1 per state variable, sharing a common hidden architecture. Physics loss enforces all 13 ODEs at hundreds of collocation points. Data loss matches observed tumor volume and clitel counts. The neural network's inductive bias, smooth-bounded outputs, constrains the non-identifiable parameters to physically plausible ranges. PINNs aren't magic, they have challenges. Balancing data loss and physics loss requires tuning lambda, too much physics weight, and the network ignores rare, but real data deviations too little, and the solution violates the ODEs between measurements. Stiff ODEs, systems with fast and slow timescales, cause training instability because the physics loss has gradients on very different scales. Solutions: adaptive lambda that adjusts during training, causal training that respects the time direction, and curriculum learning that starts with easy dynamics and progressively adds complexity. These are active research areas. PINNs extend beyond pharmacokinetics and XP. Computational fluid dynamics, simulate blood flow in patient-specific arterial geometries constrained by Navier-Stokes equations. Cardiac electrophysiology, infer conduction parameters from sparse electrode measurements. Tumor growth modeling, combine imaging data with reaction diffusion equations. Epidemiology, SIR models with partially observed case counts. The common thread: you have governing equations from domain science and sparse, noisy observations. PINNs combine both. The apprentice uses the data and the textbook. PINNs encode physical laws in the loss function. AutoDiff provides exact ODE residuals. Collocation points constrain the solution everywhere. Non-identifiable parameters gain practical identifiability through neural regularization. Your GBM QSP model with 3 stubborn parameters is a natural PINN candidate. Wherever you have equations plus sparse data, the apprentice with a textbook outperforms either alone.